So to set the scene, let's imagine that you're at a wedding reception and you have a DJ who, as DJs typically do, make a lot of noises with their mouth as they talk into a microphone. They're also playing songs. Let's say they're very old school and they're playing songs off of a vinyl record. And typically they'll have some kind of mixer where they can add the sound of their voice to the sound coming off of the record based on some sliders or whatnot. Now, suppose that they want to change the quality of the sounds that they're producing here, a graphic equalizer. So these are still used in professional audio engineering contexts and live settings quite a bit. But when I was a kid, they were quite often seen in home stereo systems. I think they've gone out of fashion. If you see these nowadays, it might be a menu in your smartphone for your playback or something. So what these graphic equalizers let you do is they let you set the relative volume of different frequency bands. So you could pump up the mid-range and drop the bass, or pump up the bass or pump up the treble or whatnot. Now suppose the DJ bought two of these and set them to have the same setting and put them into a mixer and got some output. Well, they could save some money because these are, in fact, linear systems. And as we'll see in a second, this gives them a good deal of flexibility. Because the equalizers are linear, the DJ can first take their voice, take the music coming off of the LP, add them together, and then send that signal through a single graphic equalizer, again with the settings set as they were before, however they were set before. This is just conceptual. And what they're going to get out is the same thing. So they can swap the order of adding the signals together and processing it through the system. But they can only get away with this because the system is linear. Let's look at this a little more abstractly. So a system that is linear has to have two properties. One is called superposition, and the other is often called homogeneity if you want to be fancy. It's also called the scaling property, and I like to think of it as a volume change property. So first, let's look at superposition. If I have two signals, x1t and x2t, imagine that I run each of these through a copy of some system. And let's say it's a happy system. But these two systems are identical. I can take these signals coming out of the systems, let's call it y1t and y2t, and I can add them together and get an output. Now, if the system has the property of superposition, then I can rearrange the systems as thus. I could take the signals x1t, x2t, I can add them together, and then I can run the result of that addition through one of these systems. These two results, let me call this yt here, these should be equal. So that is the property of superposition. So that was a look at the superposition property. Let's take a look at the scaling property. To satisfy the scaling property, what we need to be able to do is take the signal, place it through the system. Let's call the output here yt. And then we should be able to multiply that output by some constant, say alpha. That's going to give us alpha yt at the output here. Or I should be able to multiply it by alpha first. So this is going to give us alpha xt. And we run it through the system here. And the question is, what comes out? So let's generically call this y tilde t, because we don't know yet. But if this y tilde t equals the alpha yt that comes up here at the top, then we'll say that it has this scaling property. So we should be able to scale the signal, run it through the system, or run it through the system and then scale it and get the same thing out. So let's look at some examples. Let's take a look at a system that squares the input. So imagine that yt is the output, and it takes the input and squares it. So this kind of notation means something like this, just to be a little more explicit. All right, so let's check that superposition property. If we take x1 and run it through the system. We take x1 and square it. And then we'll take x2, run it through the system. We take x2 and square it. And then we add the resulting outputs together. So this is the situation where we're running it through the systems first. And then we're doing the addition. Okay, this is probably the worst graphic ever made in the history of YouTube. Anyway, now let's try the situation where we add the signals together first and then run them through a single copy of the system. So in that case, we'll add the signals together. I've got my x1t. I'm adding in the x2t. And when I square these, okay, well, I'll get the square of the first term. And then I'll get the square of the second term. So good so far. Oh, but look at this. Now I've got another term. I'll have cross terms. I'll have twice this x1t, this x2t. So I have a term sitting here that's not present in the situation we're seeing on top. So this fails the superposition check. So there's no this is not superposition-y. Not superpositioning, not superposition-ish. Anyway, it does not have the property of superposition. So it's not linear. So while we're at it, just for fun, let's go ahead and check that scaling property. So if we scale the signal first, and then we square it, we get the 2 distributes like this. So I have alpha squared, and I'll have the x signal squared. That's what happens if you scale it first, and then you run it through the system. Here's our happy system. All right, now what if I take the signal and run it through the system first? So I'm going to run it through the system, and then I'm going to do the scaling. Let's see what happens here. Okay, so I'll run it through the system squares it, and then I multiply it by the alpha. Ah, I see that these aren't the same. I have an alpha squared here. I have an alpha here. So this does not have the scaling property. Sometimes people will try to check both the scaling property and the superposition property at the same time. And in this example, that would run something like this. You could take your x1, scale it, take your x2, scale it by something else. So here we'll use beta. And then in this case, we'll square it. So this is doing the addition and scaling first. And what we get out is going to be alpha x1t, square everything, beta squared x2 squared t. So everything here is squared. And then I'll also have the cross terms. So I'll have alpha beta x1t, x2t. And then I can have the situation where, okay, well, I'm just going to square everything first. Each of these individual things, I'm going to run it through the system first. So here I would say I've got x squared, I've got alpha squared x1 squared coming out. And then I add to it the result of running this second term then on the system. So I'll get b squared x2t coming out. And again, I'll notice these aren't the same. I have a cross term here that isn't present down here. Okay, let's do a second example. And this one's a little bit conceptually tricky, although it looks fairly simple. Suppose we were to take a signal and add 5 to it. At first glance, might think, oh, this looks linear, quote unquote. Well, let's check it. Let's try checking out the superposition property. So if we were to take an x1 and run it through the system, what happens to it? We add 5 to it. Okay, now let's separately run an x2 through the system. So what happens when we run x2 through the system? Well, we add 5 to it. So I take the outputs of these 2 copies of the system and then I add them together. And now let's compare that to what we get if we add our x1 and x2 first and then run it through the system where we add 5. Oh, so now we see here's where the problem lies. Down here I'll have x1 and x2, but I'll have a 5 here. And up here I'll have an x1 and x2. Oh, but look at this. This 5 and this 5 add together. So although I'll have the x1 and the x2 I'm expecting, up here I get 10 because this 5 appeared twice. So this is not a linear system from the standpoint of the way we use the word linear to describe a property of a system. What makes this confusing is if you look at this, you think of this, well, this looks like a line. If we draw x of t and y of t like this, it looks like it's got a y-intercept of 5. And I'm at the edge of the screen. Anyway, hopefully you get the idea. You know, it looks like a line. It looks like a thing that is linear in the sense that there's a line here. But it's not linear in the sense of the system property. So having this extra constant sitting out here, this does have another name. It's not linear, but it is affine. And these kind of transformations are used a great deal in computer graphics. If you are interested in that, you could check out the GPU Programming for Video Games course that I'm also posting materials on YouTube. This is not a showstopper by any means for using the techniques of this class to analyze a system along these lines, because you can certainly subtract this constant, use all of the theory from 3084, and later add the constant back in if you need to. I can move this down. So let me move this down here, and now I can extend this graph a bit more. Okay, so stepping back a bit, let's speak intuitively for a moment. Basically, if you're thinking about linearity, you have to focus on what's happening with the x's that appear in your expression. So let's say we had something like this. X of t plus x of t minus 5. Okay, that's fine. Everything here is still linear. What if I add a 3 in front of here? Well, that's still fine. I can mess around with the t's in various ways, but I need to be able to have x somehow appear in all the terms that form this expression. Things like integrals are linear. Things like taking a derivative is a linear operation. And it makes sense because if you think about it, what are these things doing? You could represent them as scaling and shifting various bits of the input and then adding them together. The thing that will mess up linearity is if we were to add, and again, I'm going to use the bad color to indicate that this is making something that is killing linearity. What if you took something and square rooted it or cube rooted it? Anything strange like this is going to mess up your linearity. As one last puzzle, what about this? This is kind of a nihilistic system. No matter what you put in, you get 0 out. Well, this is perfectly linear. So here, remember, if I run it through 2 copies of the system, and I get 0 out of each, and I add those zeros together, I get 0. Whereas if I were to take any signals and add them together, no matter what they are, and then run it through the system, I get 0. So this is linear, although it is not a very interesting system. But if I were to take yt of, say, let this equal 3, okay, well, this is not linear for the same reasons we saw in example 2. You would get 3 in one instance, 3 in another instance, and if you add them together, you get 6, which is different than adding your signals together first, running through the system and getting 3. Similar issues happen with the scaling property if you go back and check that. So there's a couple more specific examples I would like to do that are particularly interesting. The first one I'm going to do is a problem in a book by Lathy. And here's the idea. We're going to have a system where the output is equal to the square of the input divided by the derivative of the input. Now, this is fairly suspicious already because I have a square sitting here. The first example I did was a square where we saw it was nonlinear. And I've also got a division, and divisions are going to be suspect. But let's take a look at what happens here. We have 2 things we need to check. We've got the scaling property, and we have the superposition property. So let's check the scaling property first. So suppose I multiply x by a first. All right, so if I did that and I square it, and in the denominator, well, a just distributes through the derivative, so I'd have a times the derivative of x of t. So this is what happens if I take the a first. I'm going to wind up with an a squared out here, xt squared. But notice that an a in the denominator is going to cancel with an a in the numerator. So what happens if I run it through the system first and then square it? Well, in that case, I would have the effect of running through the system, which is the x squared t, and the derivative. And what happens when I then multiply by a? Well, I get an a out. And lo and behold, these are actually the same. So this does satisfy the scaling property. So that's kind of interesting, isn't it? So next, let's look at the superposition property. So I'll plug in x1. So this is the result of what I get from the system if I plug in x1. Let's add to it the result I get if I plug an x2 into the system. All right, so that works out. Now let's instead add my x1 and x2 together first, and then run that through the system. Okay, so it's clear what's going to happen here. The derivative will distribute through. The denominator will wind up being the same, but the numerator is going to have this extra cross term. So this is going to give us all of this stuff in blue, but now I'm also going to have x1 times x2 cross term that'll have a 2 sitting here in front. So this doesn't match up. So although this system here satisfies the scaling property, it does not satisfy the superposition property. So it's not linear. Okay, I would like to do one last example here. We'll call this example 4. Here our system takes the real part of the input. So we haven't used complex numbers very much yet in the course, although they will play an absolutely pivotal role later, just as they did in ECE3086. We have the two properties that we need to check. We've got the scaling property, and we also have the superposition property. So let's check superposition first. So if I have my signal, x1 of t, and I ask what's its real part, so I'm running x1 through the system first, and then I have my signal x2 of t going through a second copy of the system that says, okay, let's take the real part of that. That's fine. Well, the question is, how does this match up against adding these signals together first and then taking the real part? Well, what does the real part do? It kills off the imaginary part. So there's no imaginary part here, no imaginary part here. Think about what it means to add complex numbers. You're adding the real parts and you're adding the imaginary parts. This just kills off the imaginary part. So these are in fact the same. I should probably do something to indicate that this is not a division operation. This is just me splitting the two different parts. So anyway, the orangey part here is in fact equal to the yellow thing I drew. So it in fact satisfies the superposition property. So I'll say yes on superposition. All right. Now what about the scaling property? This is the part that gets a little bit tricky. So now let's check the scaling property. So here I have to be a little bit careful with my alpha because I'm dealing with complex numbers. So I have a real part of my alpha and I have an imaginary part of my alpha. So alpha is equal to this real part, and to really write it like this, I need to put a j in front. So in this class, we're going to use j instead of I for square root of -1, our imaginary number notation, to fit with the tradition of electrical engineering. If I take my x of t and I multiply it by alpha first, and then take the real part, let's see what happens. So x of t itself, I need to write in terms of its imaginary and real components. I'm going to multiply that by alpha, which again has a real component and an imaginary component. So when I multiply these things together, I'll have the real part of x of t times the real part of alpha. And then I'm going to add to it the real part of x of t times the imaginary part of alpha. And this term here, actually, let me write this a little bit differently. This has a j on it from this imaginary part here. So what about the next terms? I'm going to have j times the imaginary part of x of t times the real part of alpha. And I need to add to it the imaginary part of x of t times the imaginary part of alpha. And now I need to actually, I need to be careful here, don't I? Because here, each of these things has a j. So this is actually a subtraction operation because j times j equals -1. Okay, that was a lot of work. All I've done here is I've done the multiplication of alpha times x of t. That's all this really is. Now, I need to take the real part of it. So when I take the real part of it, I'm left with real part of x of t times the real part of alpha. And then let's see, these have j's on them, so they go away. And now I'll subtract the imaginary part of x of t times the imaginary part of alpha. So this is actually what I get once I've gone through the real part operation. This is the real part of alpha x of t. So that was a lot of work. Now let's go the other direction. What we're going to do is we're going to take the real part first and then multiply it by alpha. All right. So let's take the real part of x of t, and then I'm going to multiply it by alpha, which is going to have two components. It's going to have a real part of alpha plus j times an imaginary part of alpha. So let me go ahead and multiply this through. So I'll have the real part of x of t times the real part of alpha. And now I'm going to add to it. Oh, I have to be careful. There's a j here. There is a j. Let me not forget that j. The real part of x of t times the imaginary part of alpha. All right, so let's compare these things. If we look at what we have on the top here, this first term matches. But the second term doesn't. The second term has this problematic thing with the imaginary part of the x of t here. Oh, let's finish off that parenthesis. Okay, there's no equivalent imaginary part of x of t down here. The other thing is this is going to be a real number. There's a j sitting here, and there's certainly no j sitting around up here. So although the first term matches, the second term doesn't. This is a huge problem. We have a case where the superposition property is satisfying, but the scaling property is not. So the real part operation is not a linear operation. Now it's sort of almost-ish. It's quasi-linear. There's probably a term for this. Because if A is real, then these do match up. Oh, you know what? I switched from alpha to A some point during the writing of this. Sorry about that. Let's make all this look more alpha-y. Alpha-y, alpha, alpha, alpha. I should say if alpha is real, then these do match up. But if alpha is imaginary, there's a problem. And from a theoretical standpoint, all of these system properties have to be true for any set of inputs you can think of. It doesn't theoretically make sense to say that it's linear or time invariant or causal only for certain inputs. Now, as a practical matter in real life, no real system is strictly linear. A resistor will be pretty close to linear up to the point that you're passing too much current through it and it gets hot and it explodes and smells bad. In which case it turns into this nihilistic system fairly quickly. So things are linear, but they're typically linear within a particular reasonable operating range as a practical thing.